So in the previous lecture, we have introduced a linear state model. And you know already one model, which is the transfer function. So maybe if one meaningful problem is what is the relation between both models? So given a transfer function, I should be able to find a state model that is equivalent to it, in the sense that it conveys the same input-output model. And given a state model, I should be able to find the corresponding transfer function. Well, if I give you the state model, the transfer function is unique. But the opposite problem or the converse problem is not unique. The solution is not unique. I mean, I can give you a transfer function, and you can give me many different state models with the same transfer function. We will see that actually, given a transfer function, there is an infinite number of state models with that transfer function. Okay? All the states are related by a geometrical transform that amounts to multiply the state by an invertible matrix, a square and invertible matrix. But we will see that in due time. So I will start by considering the problem of, given the state model, finding the transfer function. So I have a slide on that, but instead of showing you the slide, what I will do is to appeal to you to help me. So let me share the whiteboard. Let's see if it works. This whiteboard is quite temperamental. Okay, so I have a state model. X dot equals to A, X plus B, U. And Y equals to C, X. Okay? Now, I want to find the transfer function. So to find the transfer function, what is the first thing that I should remember? Let me make you a similar question. Suppose that I ask you whether scribble Z is yellow. What is the first thing that you need to know? The question is scribble Z, is scribble Z yellow? So what is the first thing that you need to know to answer this question?
What is scribble Z?
What is scribble Z? So I ask you, what is the transfer function associated to the state model? What is the first thing that you need to know?
What is a transfer function?
What is the transfer function? So what is the transfer function? What is the definition of transfer function?
A function that connects the input to the output.
Can you be more precise? It relates, yes, the input and the output in the domain of what?
In the S domain.
In the S domain, so in the Laplace transform domain. So
yes,
what is the precise definition of transfer function?
The precise definition. I think we could say it's a function function in the S domain that, when multiplied by the input, we get the output Y, maybe.
Okay, it's not exactly that. So if you divide, first, you don't speak about the input and the output in each domain, in time or the transform.
In the transform.
In the transform. So, and instead of speaking, you said something which is true. If I multiply the transform, the Laplace transform of the input by the transfer function, I get a Laplace transform of the output. So the transfer function is the quotient of the Laplace transforms of the output and the input, but there is still one detail with zero initial conditions. Don't forget
Yes.
that, okay? Because otherwise there is another term. Okay, so remember this: the definition of transfer function is the quotient of the Laplace transforms of the output and of the input, but with zero initial conditions. So what should we do based on this definition?
We should start by putting the input, the output in regards to the input.
I could not understand you.
We should start by getting a single equation with the input in regards to the with output in regards to the input.
I could have solved it, but maybe if I work with a Laplace transform, maybe it's simpler. So you want to get y of s divided by u of s. So what can we do? Instead of, I could get a solution and then apply the Laplace transform to the solution. Okay, and you should get a solution of x because from x it's very easy to find y. You just multiply by c. So I should solve the first equation. Do you know how to solve it? Yes or no? The first one. Your silence tells me something.
I don't think so.
You don't think so. So you don't know it at this moment. Okay? We will learn how to solve it. So, but maybe playing with a Laplace transform, we can get the answer to this problem without a solution. Okay? When facing a problem, try always to use what you know, and only afterwards use what you don't know and you look to forward. Okay, so let's try to use what we know about the problem. So what do you suggest me to do in relation to the Laplace transform here? No suggestions?
We applied the Laplace transform in the first equation.
Okay. But remember the last detail of the definition of transfer function? It
With
was zero initial conditions. So yes. I apply the Laplace transform to this equation. So what do I get? What is the Laplace transform of x dot with zero initial conditions?
Sx equals
Sx. Okay, and capital X means the Laplace transform.
Yes.
So my notation is capital X is the Laplace transform of small x. Okay, this is the time domain and this is the S domain. So Sx, it would be minus the initial condition, but the initial condition is zero. So this should be equal to what? The Laplace transform of Ax plus Bu. But A and B are matrices and the Laplace transform is linear. So this should be what?
Maybe Ax.
A, it's linear. Okay, so the Laplace transform of Ax is A times the Laplace transform of x. And the sum is also, you can interchange it with the Laplace transform. So this should be also be u. Okay? Now, I want to solve this equation with respect to x. What should I do? Because if I have x, then I can multiply by C and they get Y of X.
We put x all in the same part of the equation. And
Okay, S, what should I do? Tell me, right, S and then?
S minus A times X equals BU.
Times X equal to BU. Do everybody agree with this?
It misses the identity.
Sorry?
X, S must be multiplied by the identity.
Why so?
I suppose.
Why so?
I don't think it's a matrix.
Yes, S is a scalar and A is a matrix. So you, as it is, this is incorrect. So, but you can put here I. Okay, you see that my hand has an oscillating mode that is damped for the moment. And well, you could also have written here I without problem because IX is X. So writing X or IX where I is the identity is the same, okay? And now X is what? I'm sleeping.
BU divided by SI minus A.
Okay, but this is a matrix, so you don't divide, you compute what?
The inverse.
The inverse.
Multiply the inverse, yeah.
You multiply by the inverse, you get the identity on the left, and on the right, you get SI minus A inverse BU. What about the transfer function? What should be the transfer function? So my system is, I get a nu of S.
Maybe it is C times BU times.
So, and your conviction is because Y of S is what?
Y of X is C times X.
C times SI minus A minus 1 BU, that's right. That's
Yes.
C times X. So the transfer function is what?
C times SY minus A inverse times B.
Okay, so we get the transfer function. Okay, and look at this. So the transfer function is this stuff here. Look at this. We could compute this transfer function using the definition. Okay, remember that story of the Scubbles. When you want to know some property about something, not only in mathematics, first you have to know what is the something that you want to know about. Okay, if you want to know the color of Scubbles or decide whether the color is yellow or blue, you must know what is Scubbles. So look for the definition of Scubbles. Okay, whatever Scubbles might be. Okay, so any question about this? Actually, I have a slide, so let me clear this stuff here. And let's go back to the slides. Sorry. So this slide has essentially what we have done before, but I think it was better that we could do it with some effort, not just showing the slide. Now, let me tell you some exercise. Well, first, if u and y are scalar, the transfer function must be a scalar function of S. So C is a row vector. Then you have a matrix, which is this inverse of Si minus A. And then you have a column vector. If you multiply this matrix by the column vector, you get a column vector. So you have a row vector, C, times a column vector, which is what is next. So if you might multiply a row by a column, you get a scalar. Okay, so this is a scalar. Be careful with the dimensions. Okay. Now, there is a formula for the inverse, which is the adjoint matrix divided by the determinant. Probably at this moment, you don't remember how to compute the adjoint matrix. I will give you one example how to compute the adjoint matrix, but let's for the moment assume that you know how to compute this adjoint matrix. And the determinant is a scalar. The determinant is a scalar. Now, if you use this formula on the expression for the transfer function, what you get C times the adjoint of Si minus A, Si minus A times B. Now, again, this is a scalar that it is formed from C, from B, and from this adjoint matrix that depends on S. So this is a polynomial in S. Okay? And then you have another polynomial in S, which is the determinant of Si minus A. Okay? Now, you are used to transfer functions, rational transfer functions of finite dimension linear systems, in which you have a numerator and a denominator. What is the name of the roots of the denominator of a transfer function? So I give you a transfer function, it has a numerator and a denominator. And the roots, that is to say, the values of S that make the denominator be zero, these values have a name.
Zeros.
False. Denominator, right?
Denominator.
False.
Lower floor. Lower floor.
False.
Poles. Yeah, the poles. And the numerator. So the upper
The
floor.
zeros.
Zeros. Okay. The roots of the numerator are the zeros, and the roots of the denominator are the poles. Now, you see something which is quite interesting. The poles only depend on matrix A, but the zeros depend on matrix A, B, and C. Okay, so the poles, somehow they define the personality of the system, whether it oscillate or do not oscillate, and so on. Remember that if you want to describe in general the response of, suppose that you have a system, a linear system, and you put at input an impulse, that's a kick, okay? You kick it, dá pontapé na entrada, é equivalente a impulso de Dirac, okay? So what is the type of response that you are expected to find? In relation to the poles. You had one semester about this stuff. Probably it was too much. You will find exponentials. It will be a sum of exponentials of poles times time. Okay. Some of these poles are real, so you have real exponentials, either decreasing for asymptotically stable systems or increasing for unstable systems. But you can also have pairs of conjugate poles, of complex conjugate poles. In that case, you will have exponentials of the real part multiplied by sines and cosines. Okay? So the poles actually determine the type of response. If you have only real poles, you have no oscillations. If you have imaginary poles, pure imaginary poles, it oscillates without decreasing. If you have a pair of complex poles in the right half plane, so with a negative real part, then you will have damped oscilations, oscilações amortecidas se os polos estiverem à esquerda. o semiplano complexo esquerdo, and so on. So the poles determine the type of response that you can get in linear time invariant systems, because the response, remember this, the response is made of a sum of exponentials of the poles times time. Okay? As respostas dos sistemas lineares invariantes são combinações lineares de exponenciais dos polos vezes o tempo. Lembrem-se disto sempre. Okay? That is why we say that for a system to be asymptotically stable, all the poles have to be on the left-hand side, because then you have negative exponentials. So you have the exponential of minus something, okay? That decreases, goes to zero. So the transients are dying out. Now, what we are seeing is this response very interesting. The poles only depend on the matrix A, because the poles are the roots of the determinant of Si minus A. Okay? So the matrix A is what I used to say that determines the personality of the system, whether it oscillates, whether it is stable or unstable, and so on. Now, the zeros depend on all of them. And physically, this has an interpretation, because the zeros have to do with the way the system interacts with the outside world. And so C depends on the sensors, B depends on the actuators. Okay? So the sensors and actuators, together with the personality of the system, they define the zeros. But the poles depend only on A. Any question? Everybody understood this? Okay. Deep silent means yes. It can also mean no. I assume it's yes. Okay. There is one name that you should remember. I think that you have studied this in linear algebra, but this polynomial, determinant of Si minus A, is the characteristic polynomial of matrix A. Okay? Polinômio característico da matriz A. Okay, now, a note on linear algebra. Suppose that you have a matrix M with general element Mij, and the adjoint is the transpose of the cofactor matrix. What is the cofactor matrix? At each position Ij, you delete the row I and the column J, and you compute the determinant. And you form this matrix, and then you transpose it, okay? This is the matrix of cofactors. For instance, if you have a 2x2 matrix, now, to compute the adjoint, so let's start with this element. What should you place here to compute the adjoint? So this is the element 1, 1. So you delete row 1 and column 1, and you get a D. Now, you have to multiply it by -1 up to I plus J. I is 1, J is 1, so -1 to square is 1, so it's just D. Now here, I is 1, J is 2. So delete first line and second column, you get C. Okay, you get C. So you should put -1 up to 1 plus 2, which is 3, so it's minus C. But remember that at the end you have to transpose things. So the minus C appears here, and so on. So usually what I do is I compute the matrix of cofactors, so the story of deleting rows and the columns, and computing the determinants of what is left and multiplying by -1 up to I plus J, and then in the end I transpose. Okay? I think I have here one example of a 3x3 matrix. So I leave this to you to study at home. Any question? Of course, if you have a matrix of 4x4 or 5x5, you will rely on MATLAB on your calculator machine, handheld computing machine. But it's impossible. It's important that you know that these formulas exist. Okay, so this is a definition of poles and zeros. We have just seen it. Suppose that I have matrix A is this one, matrix B and matrix C. So I compute Si minus A. The inverse of Si minus A is the adjoint divided by the determinant. Okay, and the determinant is S plus 5 times S minus 1 times 6, which is plus 6. Okay, and then I have to multiply on the left by C and on the right by B to get G of S. And if I do all these computations, I get all this stuff here amounts to 1. Amounts to 1? Probably. Okay. Should be. Now, before we proceed, any question about this story of from the state model computing the transfer function? If not, then we'll consider now the opposite problem. So I give you a transfer function and I want to compute a state model such that if you compute the transfer function, you get this transfer function that you specified. Okay. In this case, finding the state model from the transfer function, the answer is not unique. Before, to each state model, there is only one transfer function. Now, to each transfer function, there are several state models that correspond to it. Okay. And you can have what we call different state realizations. Okay, so let's start by considering systems without zeros. So I have a constant that can be 1 or some constant in general. Should not be 1, could not be 1. And I use what we call phase variables, variáveis de fase. Okay? This is inspired somehow by physics. So I take as state variables the output and its first n minus 1 derivatives. So in this case, n is the order of the system, which is the order of the denominator and the number of poles, and it's 3 because I have a third order polynomial in the lower floor. Okay. So I will take as state variables the output, the first derivative, and the second derivative of the output. Okay. Now, the first thing that I'm going to do is to get the equation, the differential equation of order 3 that corresponds to this transfer function. So I use the Laplace transform again. So I know that y is gu. So I use this expression for g, and I get this expression for relating y and u. Is this too fast for you? Should I do some computation from here to here? Or no? Okay, so this is just simple algebra. And now I use the definition of Laplace transform. So s cubed times y of s corresponds to the third derivative of y in time. Okay, and the same for s squared, ys, and so on. So I got the differential equation that corresponds to this transfer function. Now, I will repeat it here. And now I use the definition of the differential equations of the state variables that I have proposed. So the first state variable is the output, the second is the first derivative, and the third is the second derivative. Okay? And I have a third order system. So I have derivatives up to order 3, so I need 3 state variables, no more than this. Okay, so first I observe that x2 is y dot, but y dot is the derivative of y, and y is x1, so x2 is x1 dot. So I got immediately one equation. X1 dot is equal to x2. It's an equation for the state variable x1. Now, x3 is y double dot, but y double dot is the derivative of y dot, and y dot is what? Is x2. So this is x2 dot. Okay, so I got the third equation, the second equation for x2. X2 dot equals to x3. So I have one equation here for x1, another equation for x2. Now I need a third equation for x3, and I cannot go on because this stops here. I already had 3 variables. So to get the equation for x3 dot, what I do is to use my differential equation that is equivalent to the transfer function. So I come here to the top and I say, well, y is nothing more than x1. So I put here a3 x1. X dot is x2, a2 x dot. And y double dot is x3, so a1 x3. And this is what? This is the derivative of the second derivative of y. And the second derivative of y is nothing more than x3. So this reads the derivative of x3. Now I solve it with respect to x3 and I get this final line here. Is this clear? So this equation, and this last equation define the state model. Okay, you can write it in particular in a matrix form. So remember, what have we done? What have we done? You start with your transfer function. Now you solve for y as a function of u using the definition of transfer function. You know that y of s is g of s times u of s, so you get this. Now you apply the definition of Laplace transform and you map this to a differential equation where you have a power of s is a corresponding derivative with some order of y. Okay, and now you define variables that are the output and the derivatives up to order n minus 1, well, where n is the order of the system. So in this case, the order is 3, so you stop at y2. The first equations come from this definition of variables. The last equation comes from plugging this definition in the differential equation for the system. Any question? Now, look here again. If you had a polynomial, not just a constant here, you would have some, say, b0 plus b1s. Then you would have b1su, and you would have here b1 y dot. But y dot does not appear in the state model. Okay? So when you have zeros, you cannot apply this technique. So let's see what happens when you have zeros. When you have zeros, okay, this is the state model that we had before. When you have zeros, what you do is you split the system in 2 parts, one with just poles and one with just zeros. Okay? There are no systems with more zeros than poles because this would be non-causal, but this is just a mathematical trick, so we don't use it for anything apart from doing computation. So you can split this. Okay, this is non-causal, but it's okay for what we are going to do. Okay. Now, you define as the first state variable the output of the system with just poles. So I call it x1. Don't confuse x1 with y. Y is the full output. And then I select as state variables x1 and its first n minus 1 derivative. So this is exactly the previous problem. And you get matrices A and B in this way. Now, y is b0 s x1 plus b1 x1. Okay, but s x1 in time is x1 dot. So y in time is b0 x1 dot plus b1 x1. And x1 dot is by definition x2. So y will be b1 x1, b0 x2, and 0 x3. Don't forget the 0. That is to say, the zeros in this technique define this matrix C. So matrices A and B will depend only on this first part, and the C matrix will depend only on the zeros. Questions? So at this moment, we know if I give you a transfer function, you give me a state model. If I give you a state model, you give me a transfer function. Okay? Now, let's suppose that I do a change of coordinates. Okay? Let's suppose that I do a change of coordinates. Changing the coordinate systems is quite important. If you change your point of view, you may transform a problem which is very complicated, turn it into a very simple problem. Let me show you one example. So that you remember this. About 2,000 years ago, what was the political regime in Portugal? We were integrated, the part of the world that is now called Portugal was part of what? 2,000 years ago.
The Roman Empire.
The Roman Empire, and the Iberia Peninsula, the Iberic Peninsula, Iberia, the spelling of the Romans, were divided in 3 provinces. You know the names? One for sure you know. That corresponds to part of Portugal and also part of Spain. But you usually say, well, Portugal, it's that part of the province. You know the name?
Lusitania.
Lusitania, okay? It was Lusitania, Bética was the southern part, and Tarragonenses was the northern part, okay? So we would be living in Bética. Now, imagine a Roman kid, and he had to solve problems like this. Multiply 31, or let's do it, 36 by 52. And you want to multiply. Okay? You can imagine that the poor Roman kids were always being beaten by the teachers. Okay. Now, the Arabs came. You know when did the Arabs came to the Iberian Peninsula? Actually, there is a battle, and the year. You know, you have you know when was that? 711. Okay, they entered the peninsula, and there was a big battle that marked the expansion of the Arabs in the Iberian Peninsula in 711. So The Arabs brought something that helped very much the Roman kids. So you can imagine the Arab kids doing Erasmus at that time. So the Arab kids were multiplying 36 times 52. Multiply, okay? So what do you do here? You do a change of representation. In a sense, a change of coordinates, okay? And this problem, you could not do it, but now it's very simple. 2 by 6, 12, 2 vezes 6, so I only know how to do this in Portuguese. 2 vezes 6, 12 e vai 1, 2 vezes 3, 6 e 7, 5 vezes 6, 30 e vão 3, 5 vezes 3, 15 e 3, 18. So 2, 7, 8, 1000. And then the Arab kid was passing. So you have a change of representation, a transform, and then the inverse transform. And the inverse transform is to write the Arab numbers as Roman numbers. So you have 1800, the CCC, 70, okay? And something which was very difficult you do a change of coordinates, and in this way became very simple. So in many problems, and we are going to have some examples of this technique, you have a very difficult problem. So you do a change of coordinates, okay? And the problem becomes very simple because your coordinates become more matched to the problem. So you solve it, and then you have to invert the response to the old coordinates by using the inverse response, okay? So remember this stuff. For the moment, let's see only how can we do change of coordinates in the state model. So where are my slides? They are here. Okay. Actually, this is a challenge to you. Pick up your paper and pencil and solve this problem. Suppose that I write the state model, x naught equal to ax plus bu, y equals to cx, okay? And I do a change of coordinates. So I have a zeta, z, which is tx. And this is a matrix which is square and invertible. In geometrical terms, what does it mean that it is square and invertible? For instance, square. What does it mean in terms of z and x?
It preserves the dimensions.
It preserves the dimension. So if I have 3 coordinates in x, I still have 3 coordinates in z. The number of coordinates is the same. And what about invertibility?
You can easily go back to the original.
And go back if I have in z, I can go back to x. So my challenge to you, and I will give you some minutes, is get a state model for z, which is equivalent to the state model for x, okay? And I have one suggestion. So I want to find the equations, the state equations for z. Something like z dot equals to some matrix times z plus some matrix times u. And y, remember that u and y are unchanged. Y should be some matrix times z. So what are these matrices that multiply z? Okay. My suggestions is for you to differentiate z, and remember that z is tx. T is constant. Okay. if you multiply t by x and you compute the derivative of tx is just tx dot. Okay, so it's very simple to differentiate. So try to do it. I will give you 5 minutes while I read my morning newspaper. Don't bother me with silly questions. So I'm kidding you. If you want to ask questions, you should. But I will give you some minutes to try to solve this problem. Everybody, don't be. You can have the strategy, which is, well, the guy is not seeing me, so I will just drop in my hands and wait for him to tell me the solution, because you will not learn nothing. Even if you don't get a solution, struggle a little bit with your paper and pencil. Mesmo que não consigam chegar a uma solução, tentem lutar um bocadinho. E a minha sugestão é derivem z é tx, portanto, z ponto é tx ponto, mas depois x ponto eu sei que é ax mais bu, mas depois eu sei que x está relacionado com z, por z igual a tx, a ver se arranja um modelo de estado para o z. Could you raise your hands when you finish? There is a rising hand, and I will be looking at you. The idea, I'm not worried to see whether Pedro did it and João did not, and so on. The idea is just for me to know what is how many of you could reach a situation. Okay, so I'm not worried. I will not start making a plus in my notes. I have an Excel. I don't have an Excel file with your names, and then I put plus or minus or 20 or 0. Or, okay, so that is not the idea. The idea is that I just grasp some picture of how are you following me. Let me take this out from here. I already see some hands. The hands are appearing. More hands, more hands, more hands. One more minute. More hands. More hands. Okay, let's go on. So one technique is, I told you already, one thing is the definition, and the other thing is, so the definition in this case appears to what is X, what is Z, okay? X satisfies the state model, and Z is related to X by T. So this is a kind of definition of what is Z. So remember these two definitions, we are going to use it. And the other thing is use what we know, and what we know is what is here, you see. 10 participants raised hand, it was very good. So we are going to use these formulas plus the fact that T is invertible and square, okay? So I start with Z equal to Tx, and I want to get an equation for Z, so I differentiate it. Now, Z dot is Tx dot. What do I know about X dot? Well, X dot is AX plus BU, okay? Now, Z dot is expressed in terms of X, but I want to express it in terms of Z. So Z is Tx, so X is T minus the inverse of T times Z. So I put here a T minus 1, okay, Z. Now, the multiplication of matrices is distributive, so TAX is TBU. TAX, but X is T minus 1Z, so I get TA T minus 1Z. And then I have TBU, okay? So I have here a state model for Z, in which the new matrix A is TA T minus 1, and the new matrix B is TB. Now for Y is CX, but X is T minus 1Z, so it's C T minus 1Z, okay? Any questions? Okay, so let's put everything together. Now, given the state model with equations, blah, 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 I do a state transfer, and in the transformed variables, Z, the state model is this one, E, and read this as gamma, capital gamma, okay? And E is TA T minus 1, gamma is not written here, H is what? Is CT minus 1, and gamma is TB. It's TB. It's not written here, but it should be TB. Okay, any question? Now, one thing that you should prove, I'm not going to do it here, but it's a good exercise, is prove that if you have this model in X, in the X coordinates, remember that the input is U and the output is Y. Now I do a change of coordinates and I get another state model with the same input and the same output, okay? Now I can compute the transfer function. I can compute the transfer function associated to the X model. What do you think that the transfer function associated to the Z model is? Don't you have a hint? Não tem assim palpite? Diz.
It's probably the same.
It's the same. Actually,
It's
you
probably
can
the same.
prove that it is the same. It's not obvious. Well, it should be, you know, because the system is the same. What you are doing is changing your point of view. So the relation between the input and output should be the same. So I won't do it here, but I suggest you to do it at home when you study, that you compute the transfer function for z using the formulas that we have. Now, remember, the formulas for the transfer function, what are they? It was the first one that we learned this morning. Okay, this one here. The transfer function associated to ABC is C Si minus A inverted B. Now, you have, instead of A, B, and C, you have these other matrices. You have these other matrices, E, gamma, and H. Okay, so write that. Now, you have expressions that relate these matrices with the A, B, and C. There is one missing here, but it's on the previous slide. So show that the expression you get for the transfer function in the Z coordinates simplifies to the expression for the transfer function that you would get by writing it with A, B, and C. You understand the problem? Okay, so this is something that I suggest you to do at home. Okay. Now, let's, we know now how to manipulate problems. And this proves that, in particular, that for the same transfer function, since you have an infinite number of matrices that are invertible in square of some dimension, that you can have an infinite number of state models with the same transfer function. Okay? So up to now, we have solved this problem. Given a state model, find the transfer function. Then, given a transfer function, find a state model that represents it. And then, using this technique of making a similarity transform, that is to say, transforming with these matrices that are invertible and square, you can have other state models, actually an infinite number of state models. And in particular, you could do a change of coordinates and solve some problems. Okay, remember this, which is a very powerful idea. Now, we still have some minutes, so let me speak a little bit about the homogeneous equation. Okay, up to now, we were considering a model which is x dot equal to ax plus bu. So let's concentrate on, remember, this is the dynamic equation and this is the output equation. The most important one is the dynamical equation. So in the homogeneous system, I don't have an input. So I give some initial conditions and I let the system abandon. So that is to say the inputs are 0 and I only have x dot equal to ax. So let's see what are the properties of this equation. Okay, this is called the homogeneous equation. And the solution of this equation plays an important role in the solution of the full equation, the forced equation with the u different from 0. Okay. Now, the first thing is to introduce something that will give you some hint on the structure of the solutions. And let's use a very simple numerical solution method. So I approximate my derivative by the incremental difference. So I pick up a very small time increment h, okay? And I have points at times kh, so 0, 0, h, 2h, 3h, 4h, and so on. So I pick up 2 consecutive of these points, and if I divide the difference between the x's, the x on these two different time instants and divide it by h. If h is very small, then this is an approximation to the derivative of x. So I plug it here, and I plug in this there. I solve it with respect to the x of k plus 1h. Okay? Is this obvious that by approximating the derivative with this and solving with respect to k plus 1h gives this or not? If someone says, no, it's not obvious, I will give you further explanations. If it is obvious, I go on. Okay, so we have this. What does this mean? Suppose that you are at time kh. You know x of kh. So you do this computation, which is the state plus h, which is a scalar, times a x of kh, and I get the next point. From the next point, I can do the same, and so on. So this is actually the so-called forward Euler method. Okay. Now, my interest is not really in solving numerically the equation. It's to let you understand one thing. So you pick up an initial condition. You are in state space. Suppose that space, you only have two state variables. If it is a three variable system, then this would be in space. In higher orders, you cannot do a plot. So suppose that you only have two variables. So you start with an initial condition. And to pick up the next point that satisfies the differential equation, what you do, you add to this point what? H, A, x of 0. H, A, x of 0. So A, x of 0 is, x of 0 is here. Then this is a vector. You modify it by A, and you get some direction. Then you scale it by your time step h, and you get another point. Okay. Then at this other point, you move again in h, a, but now multiply a by the coordinates of the point where you are, and so on, and so on, and so on. Okay. What does this tell you? It does tell you that at each point, you are moving in a direction defined by a times that point. Okay. If h is very small, actually this becomes to a very, very good approximation. It converges to the solution. Very, very good approximation of the solution. Okay. And you are going to move in direction. So if you pick up all a grid of points, and at each point you compute ax. So at each point x, you compute ax. So you know that your solutions will be tangent to these vectors. Okay? Tangent to these vectors. So you know that in this case, for instance, you would be probably spinning. Okay? So this AX define what we call a field, a vector field, because that associates to each point in space a vector where you move. Okay? This is like an error such as the ones that you find in highways, saying Porto and Coimbra and Faro and so on. So these arrows point, where does the solution goes? In the direction of the arrow. So you are here, you go down. You are here, you go up, and so on. Okay? So you get something like this. Your solution is always tangent to these vectors. Here I've only plotted 3 points, but in general, I get a solution that is tangent to these vectors. Okay. MATLAB even provides you a function which is called quiver. Okay, you have this quiver function that allows you to plot this vector field. So you give the matrix A, and you give a range of values for X, and Quiver plots these arrows, which is quite useful sometimes. Now, if you start at a different initial condition, you will get a different trajectory. Now, you could start at any point in space, okay? And you would get many, infinitely many of these trajectories. I call it orbits, ok? Chamo estas trajetórias órbitas no espaço de estado, ou trajetórias no espaço de estado. Okay? Remember that time is running, and when time runs, you are moving along these trajectories. Okay? Now, if you have many, you will have here, I plotted not an infinite number, I don't know, 20 or something like that. And you can see that they are tangent to the phase space. So when you have all these trajectories, you have the phase portrait. Okay. Now, for the moment, we stop here, and in the next lecture, what we are going to do is to see that there is a connection between the shape of these orbits, that is to say, this is a phase portrait, the retrato de phase. So there is a connection between the phase portrait and matrix A, more specifically, eigenvalues and eigenvectors of matrix A. Okay, so by computing the eigenvalues and the eigenvectors of matrix A, I will be able to anticipate whether these orbits are going to the center or going away, or they are periodic, or I don't have any oscillation, but I only have something that goes without oscillating to the center, and so on. Okay, that's a program for next class. For the moment, we stop here. Any questions?